to mean the codomain of a function, and some people use range to mean the image. Because there's this confusion, I tend to avoid the word range altogether. So I just use codomain and image. For sets f and d, f to the power of d represents all the functions from d, the exponent, to f. So, for example, the set of all functions from the set of words in some language to the set of real numbers would be written in this way, r to the w. And note that for finite sets, the cardinality of f to the d equals the cardinality of f to the power of the cardinality of d. For any domain D, any set, there's an identity function written ID, sometimes with a subscript, the domain. Its domain is D, its codomain is D, and it simply maps each element of the domain to itself. So here's an example. It maps the integers 1, 2, 3, and 4 to the integers 1, 2, 3, and 4. It's not very interesting, but it's useful in the next definition. Now, for functions f with domain A and codomain B, and g with domain B and codomain C, the functional composition of f and g is the function which we write g composed with f. The domain is A, and the codomain is C, and it's defined in this way. G composed with f applied to an input x is g applied to the result of f applied to x. So, for example, here's a function f whose domain is 1, 2, 3, and the codomain is a, b, c, and d. Here's a function g whose domain is a, b, c, and d, and whose codomain consists of 4 and 5. Here's, when we compose them, we get this function. This is g composed with f. It takes elements from the domain of f and maps them to elements of the codomain of g. Here's another example. If g is the function that squares its input and f is the function that adds 1 to its input, g composed with f applied to x is x plus 1 squared. Now let's use composition to derive the Caesar encryption function. First, we define the function f by mapping a to 0, b to 1, c to 2, and so on. Define g to be the function that adds 3 mod 26, and define h to be the function that goes back from the integers 0 through 25 to the letters a through z. Then h composed with g composed with f is the Caesar encryption function. So here are the three functions indicated, and here's the function we get by composing all of them together. The parentheses are not needed because function composition satisfies associativity. This is what associativity means. H composed with the result of composing g with f is the same as h composed with g composed with f. Simple proof, for any element x of the domain of f, if we take h composed with the composition of g and f and apply it to x, that's the same as h applied to the result of applying the composition of g and f to x. And that's the same as applying h to the result of applying g to the result of applying f to x. And then we can unfold that to get the other form. We say that functions f and g are functional inverses of each other if f composed with g and g composed with f are defined and are identity functions. And a function that has an inverse is called an invertible function. Now, a function f from d to f is said to be one-to-one if f of x equals f of y implies x equals y for every x and y in the domain. That means that there are no two distinct elements that have the same image. So here's a picture of a function that's not one-to-one, because these two elements of the domain have the same image. a function f is onto if for every z in the codomain, there exists an element, say a, in the domain that maps to z under that function. So here's an example of a function that is not onto, because here's an element in the codomain that's not the image of any element in the domain. Now, invertible functions are one-to-one. Here's the proof. Suppose you have an invertible function f and it's not one-to-one. So there exist two elements, x1 and x2, that are different, where they have the same image, y, under f. Well, what's the inverse of f? The inverse of f applied to y is x1, but the inverse of f applied to y is also x2, by definition of the inverse. And both can't be true. A function, such as f inverse, has to have only one image for each input. So that proves the proposition. Similarly, invertible functions are onto. Suppose you have an invertible function f and it's not onto. So there exists some element, say y hat, in the codomain that's not the image of any element in the domain. Well, let's consider the inverse, f inverse. This is a function, so on input y hat, it has some output, some value x hat in the codomain of f inverse, that is in the domain of f. By the definition of inverse, that would mean that f maps x hat to y hat. But that's a contradiction, so that proves the proposition. In fact, and this is an important theorem we'll use, a function is invertible if and only if it is one-to-one and onto. The proof is fairly simple. It uses the two propositions we just saw and a little bit more work. That means that if a function is invertible, it's one-to-one and onto. We already saw that. And if a function is one-to-one and onto, it's invertible. A procedure is a description of a computation that, given an input, produces an output. So here's an example. A computational problem is an input-output specification that a procedure might be required to satisfy. For example, one that we'll look at later is integer factoring, where the input is an integer, m, greater than 1, and the output is a pair of integers whose product is m. Now, there are some differences between these ideas. Functions and computational problems don't tell us how to compute an output from an input, whereas a procedure does. And there might be multiple procedures satisfying for the same spec, so solving the same computational problem. A computational problem might allow several outputs for each input. That's true of this integer factoring problem, for example. And the same procedure can be used to compute different functions.